and energy for that. Thank you very much. Thank you. Every year the NNs becoming increasingly difficult and complex. So when you train them, sometimes the effects are quite unexplainable. The researchers say that, and the developers of NNs do not quite understand what processes are being used when you train the models, AI models. Dmitri Vetrov, the PhD in physics and mathematics, the professor and researcher of the faculty of the computer sciences of the Higher School of Economics, and the lead researcher, lead scientific employee, and the head of the group, which is from AIRI, which is called the Probabilistic Methods of Machine Learning. Dmitri, hello, great to see you. Could you tell me the situation with the training of the AI models is really going out of control, and we do not quite understand what is under the hood of the relevant NNs? Well, that's like that in a way. I'm going to talk about that in more detail. Yes, it is true that the situation is quite controversial because for the last several years there were some unexpected effects that were discovered in ML. Some people think, well, whatever, the tasks are being resolved, that's great, but as a scientist I cannot agree with such approach. We should understand what is under the hood of the deep neural networks. Now, the gap between theory and practice in deep learning is something I'm going to talk about. The interesting properties in some of the NNs, the double descent explained, and I was going to wrap up with our research in terms of forming the intuition. Where do you have this properties and effects, and how can these effects be used? This was work that was done with Yekaterina Lobacheva, Maxim Kalyan, and Maxim Lobakov. Now, the modern theory of the statistical learning tells us the following. It can give us the upper bound of the average risk, given the value of empirical risk, and it relates it to, I mean, the more flexible the model is, the higher this parameter is. In the more complicated and complex models, the complexity is higher, and there is a competition between these two parts, and that means that the upper bound estimation is being minimized, and this is the optimal difficulty of the model. If we increase the difficulty, it will decrease the error, the training error, but we will have a retraining effect. The retraining error will be larger. There were many hypotheses that were built around that. What is the difficulty of the model? What is the number of the parameters that should be used? The function, the flexibility of the model, the complexity of the algorithms, what should be the optimal parameters, and including sensitivity to small changes. And the number of parameters are being set during the training. That's the set that should be used. The current SLT considers the worst case scenario. It gives the error on the test that is achieved in the worst case scenario. What happens on practice? Any deep learning expert that use deep NN will tell you that the deeper and the larger and wider the NN is, the better it works on the test, and therefore there is a contradiction between theory and practice. The theory says that you can't use complex models because it will be overtrained, and in practice you see that the more complicated the model is, the better they work. Now, there are contradictions, and there is no response to that. There is no answer to this question, because if I look at worst case scenario, how do you do that? You take a DNN, you take a ML task, and the training sample, and the other sample. The error rate for the evolution sample will be maximized, and as for the training sample, it will be minimized. And you can see that in DNNs, there's a lot of the values of the weights with the zero training error, and these are the parasite minimum.
From the practical point of view, this is a useless point because the training capacity is pretty much null in these points. For some reason, with the currently used learning algorithms do not see this point, and the authors that studied it, they compared it with a minefield. Our optimizer, when we optimize the neural network, we find ourselves on this minefield with the points that should triple us over. But we can potentially reach the good global minimum with a pretty low error in the evolution training data sets. This is an unusual effect. No one thought this was possible, that we have these points at all, not until we started studying it. In very complex and very flexible models, the upper bound estimation for the validation error is very high, so they can be catastrophically overtrained. Another interesting effect, we used to believe that we have an exponentially high amount of global minima, but those minima are isolated. But if we want to identify a way that could link two global minima, so that along the way the training error could be close to zero, we have such ways, we have such paths that can be easily identified, and this drives us to the conclusion saying that after reaching zero train loss, there is a drift within the manifold. The space is multidimensional, it's not linear, but it's hard to say how many dimensions it has. This gives us the idea of trying to at least have a peek at the property of the function that we are optimizing for additional training of the neural network, the loss function. This is not an easy thing to do because the dimensionality could be absolutely breathtaking, and we have a shortage of tools for optimizing in this case. But even with the experiments that we have in this gigantic space, there is the manifold with zero train loss and zero training error, and clearly there is a connection there. What that means is that, for example, when we have reached the global minimum of the loss function, if we continue our training, thanks to stochastic optimizers, we can drift within the manifold. This is the two-dimensional slice, the actual loss function in an actual neural network, actual task. As we can see, the structure of the two-dimensional slice is very sophisticated, not to speak of the manifold, multi-dimensional space. In the weight space, after the training error, there is a sudden drift that is possible. Indirectly, it is confirmed by the Grogging effect discovered last year. A very curious thing. The researchers were tackling a specific task that has to do with some arithmetic algorithm with the training set and the evolutionary set. The neural set was being trained with a training data set, and after approximately 500 epochs, it learned the training data set and gave 100% accuracy with the training data set. The accuracy with the evolutionary data set was at the level of simply guessing, so the training capacity was lacking. But if we continue the process of training, and if we perform another few hundreds of epochs, then at some point the accuracy starts to grow and also reaches 100%. So we have this trained neural network with 100% accuracy with the training data set, but it is in a global minimum. But then something happens, and after a while it turns into a trainable capacity, and we increase the accuracy in validation. Another interesting effect, the double descent that I mentioned earlier. What is double descent? In machine learning, you have a task, a training data set, and you start tackling the task with neural networks of different sizes. Simple neural networks, and then you increase the complexity. And then you look at how the training error changes, the validation error changes, depending on the complexity of the neural network. At first, it all happens in full conformity with the theory. The training error decreases, the more flexible the model, the easier for it is to learn the training data set, and then as complexity increases, the risk of error increases. So we continue to increase the complexity of the model. At some point, the model is so flexible as to be able to identify the training data set without any errors, and if we continue complicating the model, the validation error starts to decrease once again. So there is this non-monotonous curve. The peak of validation error occurs approximately at the level of complexity of the model, where the model is able, for the first time, to fully, without any error, to classify, to identify the training set. After that, we find ourselves in the modern regime, modern phase. The wider, the deeper the neural network, the better it is with validation. Note this, before the peak and after the peak, we have two different situations. On the left of the diagram, we are under-parametrized, where the parametrization of our model does not allow us to identify the training data set without mistakes. We do not have enough area for maneuvering. After the peak, we are over-parametrized. In this situation, the properties of the model radically change. Let's look at the difference between under and over parametrization. First off, if the model is under-parametrized, we do not get non-zero train error. With the over-parametrized model, it's the reverse. Under-parametrized, either one isolated minimum, or they are several but isolated. With the over-parametrization, there is a manifold of minimum. Under-parametrized, the loss function is at least locally convex. With over-parametrized, it is non-convex. If you've ever given it a try, you know that in this range of global minimum, there are some problems with local convexity. And with the under-parametrized model, there is an optimal complexity level. It exists. If we complicate the model above that level, we start getting validation error more frequently. With over-parametrization, there is no such optimal complexity. The more complex the neural network, the better it performs. So it all is about the limitation of our computing hardware. Now, what is happening with the weights in the global minimum point? We know from linear models, from kernel machines, such as the support vectors machine, that the more the weight norm, the higher the functional norm. That means the norm of the function that is realized by our ML algorithm. What is the function norm? This is about the Lipschitz constant. It is higher in this case. So with all things even, we should select the rule where the weight norm is lower. This means we can higher hopes that the quality of training will be transformed to validation. Two diagrams that depict that. The one on the left is where the weight norm is smaller. The one on the right is where the weight norm is higher. So with the one on the right, we cannot really count on good training capacity. This is the case for linear models and for kernel machines, but experiments show that there is a similar effect for neural networks as well. This is why in neural networks, regularization techniques are very popular, which impose a penalty for higher weight norms. Now, let's try to use this intuition to explain the effect of double descent. Let's take an over-parametrized model, one-dimensional space, the weight parameters of an over-parameterized model. Of course, in actuality, it will be much more complex. We have not one global minimum, but a whole manifold of global minima. In the manifold, the red strokes represents the manifold. So in that space, we can find a point with the lowest norm. This is the point to which we need to come when I work additionally with the parametrizer that imposes a fine for excessive weight norm. So this is the point for zero train or error. Now let's take a model that is more over-parametrized, which embeds this model. We add weights, we increase the manifold. The old manifold is within it. If in the new manifold we try to identify the point with the zero train error and minimal weight norm, we will see that the weight norm is smaller. You can see this geometrically. In the more complex model, the weight norm is not going to increase, but in actuality it will, in almost all cases, go down. Experiments show that precisely that is confirmed by practice. If we increase the number of weights by a factor of 10, the resulting weight norm could fall by a factor of 50. So the weight norm decreases. In a trained neural network, if we use additional regularization, NTK, the weight norm decreases in a wider and deeper neural network. This also means the functional norm of the resulting rule also falls and the training capacity increases. Back to the double descent. While our model is under-parametrized, we get a certain quality. Even with the training, we have certain errors, even with a regression task. As we increase the complexity of the model, the error decreases, and at some point the model can identify the training data set accurately, but the weight norm is very, very high. The high weight norm means higher oscillation, and worse training capacity, the validation error is very high. If after that we continue increasing the complexity of our neural network, the norm of the resulting weights in the neural network starts to go down. There are more weights, but the sum norm is lower. There is less oscillation, and as a result, the generating capacity increases. The results with the training data sets start to transition to the validation set, to the evolution set. With the double descent, there is a certain intuition that helps us understand what is going on, that helps us understand that there is no contradiction to common sense. This is just a property of over-parametrized models. The property is a bit counterintuitive. The more complex models have simpler decision-making rules. That is associated with regularization. In over-parametrized models, regularization plays a different role, as opposed to classic regularization in classic ML algorithms. By adding a regularizer, we are not trying to prevent the achievement of the global minimum in our loss function with the training data set, like we do in classical models. The role is different. Among the diversity of weights that give zero loss function in the training data set, we need to identify the values that have additional benefits, that have, for example, the minimum norm. What are the types of regularization used in modern deep learning? Weight decay, L2 regularization, implicit regularization that is caused by stochastic gradient descent, stochastic optimization methods. We are using stochastic optimizers to train our neural network, because such optimizers have some gradient descent noise, which prevents us from seeing clearly the relief of our optimized loss function. And surprisingly, as it is, it also results into the fact that we end up with the weight values that give pretty good training capacity, and normalization, different normalization techniques, batch normalization, weight normalization. They all result in large-scale variability, which additionally links the weight norms to the width of the global minimum. The latter is evidently responsible for the training capacity. In the community of deep learning scientists, there is this idea, not experimentally confirmed, but there are experiments nonetheless. Wider minimums have higher training capacity than narrower minimums. You can see that on the diagram. The black function has two global minima. One is wide, one is narrow. And then there is the function that represents the loss function. The black one is for the training data set, and the dotted red one is for the evolution data set. Slightly skewed, as opposed to the black one. If we find ourselves in the flat minimum, the low training values pretty much coincide with the lower evolution values, and that is the opposite of the case we see in sharp minimum. That is not optimal. We would like to have a procedure of training that would end up in flatter minimum. Which minima are more commonplace, more widespread, flat or sharp? What is better in terms of regulation? We have some intuition that points us in the right direction. One of the regulators that helps us end up where we can converge is the dispersion of our optimizer steps. The steps are random because we are training with stochastic optimizers. The dispersion of the steps is impacted by two parameters: the size of the mini-batch and the step interval. The bigger the step interval, the higher the dispersion of our steps during optimization. But there is this analogy one can draw, is where the relief of the optimized function is not seen very clearly. It's as if we have a myopic person and we take away the glasses. They can see the surrounding world, but without any details. What does that mean? That means that more subtle details are simply not seen by the optimal. Multi-minima, there are a lot of minima, flat and sharp. In our landscape, if we start at some point and launch two stochastic optimizers, with one we use a smaller step interval and a bigger step interval, in the other one with a smaller learning rate, we see more minute details and we descend down to the very closest minimum. With a larger learning rate, we will end up in zero train loss, and with the training data set, the error will be conversely pretty high. But if we start at the same starting point and we launch our stochastic optimizer with a larger learning rate, the dispersion of our steps is bigger. In the iteration procedure, we do not see the smaller details in the optimization function, and then with a larger learning rate, the black function is seen as the dotted green line. It does not see the smaller details, but it sees the flat minimum. We will cover more ground from the starting point to the minimum, but we will end up in the flat minimum. However, in the flat minimum, we have better training capacity, so we have a lower error with the evolutionary data set. So this is the hypothesis. Just take it and test drive it. Take a neural network and try running it from the same starting point with different learning rates and see the effect. I also decided to show that apparently if we review the sharp minimum, inside of it there is an even sharper minimum, and this is clearly true for a certain learning rate. So just take this hypothesis and experiment with it, right? It's not that simple. The key challenge here for for validating our hypothesis with experiments is batch normalization.
On the one hand, we know that the batch normalization procedures simplify the training procedure. It makes it more safe in terms of the hyperparameters, and basically all NNs use normalization in its architecture. At the same time, every block of normalization makes it much more difficult to analyze the loss function, because we have the landscape variant. This is the symmetry that does not help us to link the width of the minimum with the generalization capacity. In this case, the entire network within a generalization block, it becomes the following. If we take all the ways that we multiply by some positive constant, the ways changed and the neural network remained the same. So the function that NN realized were unchanged. And so if we look at our space of the ways, we see that we have different variants that are descended. Let's take a dot where the global minimum is achieved, this red asterisk. We can estimate that. We can, for instance, use the Gaussian matrix. If we take these ways and multiply it by 100, we shifted the function. In functional terms, it's minimally equivalent, but we have this kind of a forking that, you know, widen as we go from the zero. In this case, it's very hard to say what is our optimal minimum width. It can be anything depending on the ways. And what is the hypothetical minimum width? And this is what is determined by our resolution capacity of our solution. And the geometrical width cannot be calculated here because of the variability, because the same function realized by NN can have any width depending on the ways. So the idea is, maybe we should, as a characteristic of the curve of the width of our minimum, maybe we can have a single sphere for that. And we can compare the green and the red and calculate the minimum here. This width will have the resolution capacity, but it might not have the resolution capacity of our algorithm of optimization. This is a kind of a negative attribute that is explained by the wide use of the normalization blocks. Now, what do you do here? What the weights do if we work with the large-scale NNs, with a lot of normalization blocks. In this case, for the weight norm, we have two forces. The competition between two forces. One is weight decay, tries to minimize the weight of the weights, and then the gradient from the data, the competing one. It is always orthogonal to the beam, because the function of the beam does not change, so the gradient of the data will be orthogonal. But if we make a step on the gradient for the on the data, stochastically the norm of the weights will increase, according to the Pythagorean theorem. What will happen in the weights? Well, depends which force is stronger. And if we look at the real NNs with the weights, with the weight norms, the weight norms, it changes. It either increases by manifold then the narrow minima become wider minimum, or it can be decreased, and then the situation will be reversed. It makes the analysis harder in terms of what are the functions and the attributes of the minimized losses. And to move from that point, we need to understand that the resolution value of our optimizer changes. Whatever the step. Now, how can we remove this variativity? Well, we can do that. Let's say that we train the NN with the gradient descent. You can use whatever stochastic optimizer that you like. Our ways describe the trajectory. The function is changed. You can use the singular sphere. When we project the weights for the singular sphere, and we can do that because there is a match, and you can take a point to optimize that. Now our procedures will be equal, will be the same. The step will be different. We'll have not an ether learning rate, but an effective learning rate, and we'll not have just a gradient, but an effective gradient with a singular sphere. The effective gradient is related with our parameters related to the steps. We use this formula. It depends on the current weights of the weights, but we can use the singular sphere here. Now we do not have the beams according to which the function changes. We remove these parasite symmetries that simplifies the training procedure, but makes the assessment of the landscape of our loss function much more difficult. And every time the step changes, the step value changes, and it depends on the current weights in Euclidean space. But let's look at the training procedure only on the singular sphere. And let's fix the step. We had a hypothesis that the length of the step determines the optimization step. And we can't have the situation when the narrow minimum will become a wide one, because we do not allow the weights to change. By fixing the step, we fix the resolving power, resolving capability of our solution. And let's fix the last layer with some weights. The Euclidean theorem shows that it does not have any other consequences. And you can train everything except for the last layer, and the NN will be trained. And then let's fix the last layer, because the last layer is not used for normalization, but for the experiment we want to make a full-scale NN. Then the network will be fully scalable in terms of the variance, and then we use this gradient descent. And for each gradient descent, we'll make a singular sphere, and we will train this NN with the same sample with different constant values in terms of the length of this step. The learning grid will be fixed, and the prefixed grids will be sent for the training, and then from the same point we will launch it with the same step, and we'll see what will happen, and we will remove the data augmentation. As the experiment shows, it can be reversed back. All the experiments that I am going to show now can be done. but not in a filtered way. And here it is pretty clean. Now, what is our difference from a standard DNN? The standard DNN has a lot of hyperparameters that affect the outcome of the learning, and it's hard to understand their interconnection. We have the learning rate, we have the schedule, we have the weight decay coefficient, either higher or lower. We have the initialization scale. We can take a point, a dot with a lower dot and a higher dot, and we have data augmentation, and that leads to the following: our optimization function changes all the time, and the scale invariance is not 100%, but let's say 80% is has scale invariance. The other 20% does not have. But how do you understand what is the efficient learning rate? In our simplified DNN, we removed all the hyperparameters except for the learning rate. And then we have the situation when the geometrical width of the minimum is in line with the functional minimum width. We can't change that because it's in the singular sphere. We do not have the weight decay because our weight norm is a constant. We launch with the same learning rate, and it does not depend on the initialization point. So we select a point and we launch the training procedure. So there's only one parameter that we can control, the learning rate, that we think is responsible for our algorithm optimization. This is the experiment design. We're going to launch our NN. The same sample, the same architecture for the DNN, but just the learning rates will be different. The step will be different, the learning rate will be the constant, and the results were quite interesting. Depending on the learning rate, we have three phases, three modes of the learning of our DNN. If we take a very large learning rate, our DNN goes to phase C, the divergence random guess accuracy. On the right-hand side, if we take a very small step length, the rate, we go to the zero training error rate. But if we have it somewhere in the middle, the effect is very unexpected. We do not have neither conversions nor diversions. There is the DNN has some level of accuracy. On the upper diagrams is the dependence of the NN on the learning method. In the middle part, we have the error of the training, error of the validation. On the right-hand side, we see the average of the norm of the gradient. The lower it is, the wider the minima is. And what do we see here? Let's look at the first phase. There is some range of the steps of the rate, but if you look at the right-hand side diagrams, you will see that the more the step is, the wider the range is, the wider the minimum. So in our losses function, there is a lot of minima with different width, and we can regulate the width of the minimum by selecting the rate, the width of the rate, the width of the step. The smaller it is, the wider the width of our minimum, and the width of our global minimum correlates very well with the generalization capacity. The narrower our minimum is, the higher the validation error is, and vice versa. And this is a direct dependency, and you can see that on lower diagrams. So there is a dependency here that you can see it. And it depends on the step, on the rate, on the learning rate, and we see the good dependency. So yes, you have to train with the larger rate, with a larger learning rate, learning step, so that there are no narrow minimum. And another effect is that we have gone our way through the initialization point to another point, and the step is smaller. At the same time, the global minimum is 100% for the training, and that tells us the following. That tells us that there are many more narrow minima than the wide ones. If we increase the rate, at some point we will be able to converge to a widest minimum that we have in our landscape of losses. But so maybe we should increase the step. But if we increase the step too much, the rate too much, we go from the diversion state to equilibrium state, when our DNN is working as kind of a semi-usual mode. This is the second phase. You can see that there is no convergence here. There's no convergence to the 100% in terms of the accuracy of the training. So the situation does not change in terms when we implement some iteration. There is some attractor, some negative feedback when we are in the semi-usual state. And in this semi-usual state, the interesting thing is that if in the phase we take a larger rate, we are somewhere on the heightened points, heightened levels. The validation error is higher. And by increasing the rate, we go to the third phase, where we see the full guesswork and full divergence. This is an unusual effect, and we didn't know what it is related to, and it is related to the scale variability, scale invariant function. And if we use gradient descent, if the step width, if we have some convergence down on the global minimum, and if the more parameters we have, we're going to be stabilized on some value of the losses function. This is the function attribute. Why it is important? All the learning algorithms for DNNs are based on optimization methods, and they are focused on minimization of the convex function. And basically, it would be great to develop a new optimization method that would be tailored to the fact that we have to optimize the functions, and the functions that are not convex on the local level and that have different width, global width, and in this landscape of the functions of the losses, we need to find the widest minimum. That's the goal. And given that, we have to develop new methods. Now, in conclusion, is that the current DNNs are very over-parameterized, that are counterintuitive, have counterintuitive properties, and that means that we need a new intuition, maybe. The larger models contain more simple solutions. This is counterintuitive, but I hope that I was able to explain to you why it should not be regarded as such. The normalization techniques that we currently use is the training procedure, but they complicate the study of the training loss landscape. And the loss landscape function has a lot of features, and you have to discover that, to explore them, to develop a more efficient training that will help us to find the widest minimum, because in this minima our generalization capacity will be better. Thank you, Dmitri. Thank you very much. And what of the DNN effects is the most interesting, the most promising for you? Well, I think all of them are promising, but I think the most promising is the Krokin effect that showed for the first time that even when DNN has 100% accuracy in terms of the training, some processes continue to happen, and we do not stop the training procedure. We just give 100-fold more time for the training. as for the DNN, you said that we need practical experts. And we need new practices there. Does that mean that we do not need theory? No, we do need theory. The theory just has to be more tailored for the practice. Yeah, well, theory is a kind of a food for thought here, right? Yeah, absolutely. Yeah, Dmitri is going to leave us, and next year we're expecting you to deliver some good news for us. Thank you very much.